Okay, okay, this is the problem. So find out the number of edge disjoint paths. So this is the one particular problem, which may be interesting in certain cases. Why? Because why edge disjoint? Because in a practical sense, suppose somebody want to calculate the number of edge disjoint paths, so he knows that these are actually totally distinct routes, basically. So if one route gets damaged or maybe blocked, then people can use the other route, something like that. So this is that's why this is important. Another important problem that are often discussed is that I mean, let's say I have 3 nodes here, I have 2 nodes here, and these are all connected. Right. Now, uh, if if this is all connected, but suppose this is not all connected, okay, then what happens is suppose if I if I take this node as one of the matched nodes and this node as the pair, and so this is the pair. Okay, so if I take this node, let's say this is XYZ, this is A comma B. So if I pick B first, then the other pair I choose as Y, then YB is one match. But then I cannot take, can I take any other, probably, uh, so another possible match that I can say is Z comma A. So this is another match. Okay. So match means there should not be, I mean, any edge, common edge, basically. I mean, common endpoints. So this is possible. But let's say I remove this, I draw it in such a way. Let's say I have a connection like this. So let's have these connections like this. Then what I can do is probably if I take X and A, let's say I take X comma B as the pair. So this is one matched pair I take. So this is done, this is done. What is left with me is A and Y and A and Z. So probably, let's say, I mean, I don't have this edge. Let's say I don't have this edge. So now let's say this is the connection. So if I take XB, then I cannot increase my matching further. But suppose I can have an alternate matching like XA and Z comma P. This matching is okay. But if I initially take X comma B, then I cannot my matching, I cannot increase it any further actually, because A is not connected to Z, so I cannot make Z comma A. I cannot make X comma A because X is already taken. I cannot make Z comma B because B is already taken. So if this is the picture graph that is given, then you can, this is one matching possible, this is another matching possible. But if you start with this matching, you cannot increase your match any further. But if you do intelligently, you can probably find a matching of size 2. So this is a higher matching size, so maximum matching size. So if the question is that given, remember this graph is not completely bipartite. It is a simple bipartite graph. Complete bipartite means actually every node in the left side is connected to every node in the right side. So the second problem that I'm saying is finding maximum matching in a bipartite graph. Okay, this is another interesting problem. Okay, so the idea is that these problems are very motivating and interesting problems, but it has been found. Remember that there is no such weight associated with this graph. Okay. Here also there is no such weight. I'm only interested in edge disjoint paths. There may be concept like edge disjoint shortest path. That may be concept, but that is something different. So, so all these problems people try to solve using traditional approaches like what we know, divide and conquer, dynamic programming, greedy, etc. But people fail to give quick and reasonable answers. Okay, so then came this concept of network flow. Okay, so that's why for many graph theoretic problem or transportation problems, okay, they deal with something called network flow. Often in computer network also, we can model many problems as network flow problems. So let us try to define what is a network flow problem. So first of all, we have to understand what is a flow problem. So flow network, actually, it's a directed graph. It's a directed graph. Some direction will be there. Some direction is there. And in that network, there is two special nodes. One is S and one is T. And this S is called the source. And this T is known as the sink. This is special nodes. So all the edges that are incident on S, they are actually outgoing edges. And all the edges that are incident on T, they are incoming edges actually. That means a sink, it cannot happen like CT has something like this. It cannot happen. Then this is not a sink. Sink means every edge that is incident on T, all are incoming. That means flow is coming. Flow means something, let's believe. Flow is something, and that is coming to T, and T is something infinite thing. Like whatever you give it, it will be able to consume. Similarly, AC is something infinite source. I mean, whatever, just like the sun or something, infinite source. So whatever you can generate, it can generate any large value you like. Okay. So that is the thing. And these edges, okay, that are connecting other vertices, okay, these are called intermediate nodes. Let's say A, B, C, D, intermediate nodes. And each edge, let's say this edge, AB, each edge has a capacity. Capacity means capacity of edge E. So capacity means the maximum amount of, say, something flow that it can carry. Okay, so if you think it as a pipe, then capacity you can think of as a volume. Okay, something volume of the pipe. Okay, so it is something like that, similar to that. So every edge has a certain capacity value, and we assume for simplicity that capacity is non-negative. Now, this is one important thing, and so every edge has capacity. That means this edge, S to A, every edge has capacity. Now, with this thing, the question arises that I want to give. So initially, what is the initial assignment? Initial assignment is if there is a function f, okay, there is a function f. I want to assign for every edge to some r plus. What is r plus? Some real number or something. Okay. What does this mean? This means I want to assign some flow. This is some flow value, some functional value to these edges, all these edges. Okay, all these edges. I want to assign some value subject to some conditions. So what is the input? Input is this graph, okay, directed graph with S and T. Okay, S is the source, T is the sink, and all edges are coming out of S. That means all the edges incident on S are actually I mean outgoing edges, and all edges that are incident on T are incoming edges. Rest edges can be in any direction, and flow actually moves in that direction. And every edge has a capacity. Remember, the S is infinite source, T is infinite sink. What about other nodes? There are some property I will tell shortly. So what is the idea? Idea is my job is to assign some value f, some function f. What is that? That function is, it's a map for every edge to some number, some real number, okay? And this function should satisfy some property. What are those property? Number one is capacity condition. Capacity condition. capacity condition. What is that? That means the flow value associated with every edge. Okay. See, this is the mapping I am interested to find. Goal is to find F. Okay. But what is this F? This F should satisfy some property that for every edge E, FE should be less or equal to CE for all E. That means the flow value I can assign to every edge that must not cross the capacity. It is very something natural that I cannot push some fluid which is more than its capacity. Okay, and this is actually greater or equal to 0. Okay. The second thing, second condition is called, so remember, if I assign everybody as 0, then this trivially satisfies this F. Because 0 is less than capacity, this is satisfied, capacity. The second condition is called conservation. Conservation condition. So what is this conservation rule? Conservation rule is special that except S and T, the conservation rule applies except S and T. What is S? S is the source, another is sink. T is the sink. So except S and T, the conservation rule must be satisfied. What is that? That the sum of the flow of all the edges when E is into a particular node V. Let's say V is one node like this, and so V is some node in other than S and T. So that node must be something like this, because it will have some number of incoming, some number of outgoing edges. Remember, it cannot happen, it doesn't have outgoing edges, because then it will become a sink node. Then it is not, satisfactory. Similarly, if it doesn't have any incoming, then it becomes a source node. It cannot happen. So any intermediate node must have both incoming and outgoing edges. So for those nodes, the conservation property must hold. What is that? It says some of the value of the flows of edges that is going into V is equal to some of the flow values of the edges that is E out of V. Okay, E out of E out V. I can write E out of V, something like that. That essentially means whatever flow that is going into this node, that must be equal to the flow that is coming out of this node. That means V is not unnecessarily generating or capturing any kind of flow. It is just a forwarding tool, forwarding machine kind of. It is gathering and it is forwarding. That's it. Okay. So these are the two conditions. Now, I have to, my job is to find out a function f that satisfies these two conditions. Okay, if I assign every edge 0, okay, then also this conservation is satisfied, because if you look that 0 is going in and 0 is going out, everything is 0, all 0 equal to 0. Okay, so this is satisfied. But for all other values, we have to be very careful. Careful in the sense, consider the node A here. Consider the node A here. So if the edge, I assign this edge S to A as let's say 5, then to have a satisfactory flow, I must assign values for this edge and this edge, something like 2 or 3. Then it's a valid function f. If I assign 2 and 2, then this is not a valid function because this is violating this condition, this conservation rule, because 2 plus 2 is 4, 5 is higher than 4, so it is as if storing some flow, so that's not allowed. Okay. There is another thing. So the question should be clear. Remember, these values are FE values, FE. And these FE values are essentially, I can assign any value between 0 and capacity. I can assign any value between 0 and capacity such that these two conditions are satisfied. Now, the question is what values I should assign to f. So that means what is the function f? That is the precise question. What is the function f? So basically, you can think of this is a function I need to design such that it can assign a mapping for every edge. There is a real number, and such that it satisfies these two conditions. Okay. Now you can actually design, many such functions. Okay. Let's say f1 is one such function. Okay. Now f2 is another such function. Valid functions. Valid functions means it satisfies both these conditions. Okay. F2 is another such function. Let's say in this way, I can say Fn be another such function. So there are multiple such functions possible. So which function I should be interested in? Okay, that's a big question. Okay. So for that, what we do, we define some quantity. Called V of f. So if I have defined a function f or defined a mapping f which is e to r, then I associate a value with this function f. What is that? That is sum of the f values of the edges e is out of s. Okay, this is my definition of value of the function. Okay, I can have different functions which satisfies these two conditions in the graph. Now I define a value of that function. What is that value? It is the sum of the flows that are coming out of S. So look at this graph. So I can assign many different values such that, let's say I assign this value 4. Then value of the function is 9 basically in this case. Okay. Then I can have another mapping where suppose the value here is 3, the value is 4 here. So then the value of the function is 7 basically. Remember, this value of these, the function value depends on the flow values that are coming out of S. But to become a valid function, you should satisfy all these two conditions, conservation and capacity. Okay. So once I know or I define the value of the function, which function I should be interested in? The f, I'm interested in the f, okay, that has maximum value of this function. Okay, that has maximum value for these functions. Okay, so many possible f's are possible. Many f's are possible which satisfy this capacity and conservation. But I'm interested in that f where this VF is actually maximum. Okay, so this is known as the maximum flow problem. This is known as the maximum flow problem. So I hope the what is maximum flow problem, that should be clear by this time. So in general terms, it is called that given a flow network. Remember what is a flow network? Flow network is like this. Flow network is like this. It will have a sink and a source and a sink. Source is infinite source. All the edges will always come out of it. All the edges per sink will go into it. All the other intermediate nodes can always have incoming and outgoing. Okay, and these are directed, and every edge has an associated capacity which is non-negative. Okay, and in this condition, I need to find out a mapping for every edge to some real number such that it satisfies these two conditions, capacity and conservation. Not only that, I can generate many such functions, but I'm not interested in all of them. I'm interested in the function, the f, that has maximum value of Vf, where Vf is actually clearly defined like this term. It is the sum of the assignments, function values for all the edges that are coming out of the source node. Remember, not of any other, coming out of the source node. Okay, and this is the maximum flow problem. So, so let us take an example that may be worthy to discuss. Let's say, let us take an example. So let's say this is simple flow network. This is my S and T, and the connections are like this. And there is a connection like this. And this is 20. That means it's the capacity of this edge is 20. Let's say this is A, this is B. This is, let's say, 10. This is, let's say, 10. This is, let's say, 20. This is, let's say, 30. Okay. So once I have this, so what is the best possibility? Possibility is, let's say, if I pass here, if I can assign a value maximum 20 in this link. Okay, so if I assign a value maximum 20, then I have to somehow make this edge and this edge some values, their sum is 20. Okay, such that their sum is 20. Okay, so I can do it in various ways. I can make this 10 or this 10, or I can just make this 20. Then I have to make this 0 basically, because 20 is going in and 20 is going out. So this conservation is satisfied, the capacity is satisfied. And then when this is 20, the same 20 I can allow to go through here. So I cannot push anything here, because if I push anything, it will add maybe more than 20, but its outgoing link has a capacity of 20, so it cannot happen. So I just make it 20. So 20, 20, 20, it is going like that. Okay. And this is 0, because this is not carrying any flow. This is 0, this is 20, and this is 20. Okay. So what is the, so this is one function f, okay, such that I can say, let's say I designate this edge SA as 20, f of 80 equal to 0, and so on. I can assign and so on. So what is my value of the flow? That is sum of the FE values E out of S, which is 20 plus 0, which is equal to 20. Okay. So this is one such assignment. But the question is now, can I do an assignment better? Okay. So let's try. Let's try that. So let's say instead of doing this, I do it like this. So I push 20 here, and here I push 10. Okay. So then here is 20 and here is 10. So what I can max push is 10 down here, because if this 10 and this 10 will make a 20, and that I label as 20. And then there is another 10 I can make, and this is certainly satisfactory because this has a capacity of 10, it can carry 10. So here, if this is the assignment, so this is an assignment of 20, this is 10, this is 10, this is 20, this is 10. If this is the assignment, then if this function I designate as f dash, then I can clearly say value of f dash is equal to 20 plus 10 equal to 30. So that means in the first assignment, value of f is 20. The second assignment, value of f prime is 30. And remember, all the conditions are satisfied. All the capacity condition and the conservation rules are satisfied. So I should definitely look for this value of v prime, okay, so that the value of the flow is maximum. So remember that this thing I am doing in an ad hoc manner. I mean, I am doing some trial and error, etc. But for a big network, okay, for a very big network, this cannot be done in this way. It has to be based on some algorithm or mechanism, so that I mean it should be doable in a quick manner. Some steps have to be followed. Okay, so for that we need to do it in a very systematic manner. Okay, and that's what we intend to do. So how to do it in a systematic manner? So for that, we need to understand some terminology. That terminology, let us first understand. So there are two concepts. One is forward edge. One is I mean it's some concepts like forward pushing and backward. Forward, I mean, let's try to understand this concept with this diagram. With this diagram. In the earlier case, if you go back to the earlier assignment, so what was the earlier assignment? It was like this. The earlier assignment was like this. Okay. The earlier assignment was like this for F. I am pushing here 20, 20, and 20, and these are all zeros, and this is a valid. So now look at every edge, S and A, It has a capacity of 20 and it is carrying a flow value of 20. Okay, that means I cannot increase the flow in this edge any further because it has reached a saturation point. I mean, it has reached its maximum. But look at this edge A to B. Okay, so in this case, actually, it has a capacity of edge AB is equal to 30, but flow assigned to this edge AB is 20. That means if possible, or if I wish to satisfy other, or if I wish to increase the flow, then I can actually push another 10 unit along this line. And that will not violate the capacity condition. Okay. Whether it will violate the conservation rule or not, that's a secondary question. But I can still push forward another 10 units of flow along this path because this link is not fully filled up. This link is not fully saturated. Okay. So that is the concept. So it is called that we can push forward on edges with leftover capacity. So this edge, okay, so if an edge is E, okay, and it has a capacity CE, and it has a flow assignment of FE, and if FE is strictly less than CE, then we say that it has a leftover capacity of CE minus FE. This is called the leftover capacity. This term is this leftover capacity. That means this much I can still push forward because the flow it is carrying is much less or strictly less than the capacity. So the statement here is we can push forward on edges with leftover capacity. This idea is to be understood. So those edges which have leftover capacity, we can push forward on those edges if it does not violate other conditions. Of course, it may lead to violation of other conditions, but if somehow it does not violate other conditions, I can still do that. Okay, that is called push forward. Similarly, look at this edge, SA. Okay, look at this edge SA. This edge SA has a capacity of 20, and it has a leveling of 20, which means that that I cannot push forward anything in this edge because my FE is strictly less than CE. This is not satisfied there. Okay, this is not satisfied there. So I cannot push forward. Whereas there is another concept which is known as pushing backward. Okay, pushing backward. What does this mean? That means if the concept is push back. What is the pushback? Now, if FE is less or equal to CE, but it is greater than 0, okay, that means it is carrying some flow which is less or equal to the capacity and it is greater than 0. That means it is carrying some non-zero, non-negative, positive flow that is in between the maximum capacity and 0. Then I can push back maximum FE. I can push back some quantity. Okay, I can push back some quantity, but that quantity, let's say, designate, let's say that I designate by, say, let's say X, but that quantity can be less or equal to F. So to be more comfortable with the example, so here it is carrying a quantity of 20, so I can actually push back anything between 0 and 20. Push back. So I can push back, so let's say 10, I can push back 15, I can push back 16, anything between 0 and 20 I can push back. So what does this pushback means? Pushback means I actually reduce the labeling by that amount. So if I push back by 10, the label will become, instead of 20, the label will become 10. If I push back 15, the label will become 5. That means I'm reducing it by the pushback amount. So the current value will be less. So it will still satisfy the capacity condition. Okay, no problem. So that is the concept of pushback. So pushback can be anything between 0 and the current flow that is carrying. Similarly, I probably missed one thing, that push forward can be anything between 0 and this much. So if I want to push forward X amount, let's say this is push forward. Okay, I can push forward anything which is between 0 and this leftover capacity amount. Okay, because this does not violate the capacity condition. Whether it will lead to the satisfaction of the conservation rule, that I have to see. But these two concepts we must understand. So later we will use this term, push forward this quantity, push back this quantity. There should not be any confusion with these terms. That I can push forward this much, I can push back this much. Okay. So what does it mean? That should be clear. Okay. So once these two things are there, then we can go into the actual designing of the process. So time is running out, but another 5 minutes is there. So up to this point, if any question is there, you can ask. I will start something known as, let me just give the term, something known as residual graph. Okay, so next day onwards, we'll start from here. What is a residual graph? So residual graph, you can think of a data structure, okay, needed to solve the max flow problem. Okay, so I need this data structure to solve this max flow problem. Data structure means it's a storage, okay, of data that I will use. And there I will create that data structure based on this push forward and push backward concept. Okay. So because time is less, let us stop here. So I hope I have been able to motivate the introduction of the max flow problem. Okay, where max flow is necessary, network flow problem, like edge disjoint path construction, and this maximum matching in a bipartite graph, and so on and so forth. Okay. Okay. So any questions from anybody?